Welcome to another problem session. So this really good problem. This comes from Klepper and Colin book. Uh, so here is a like a fisherman. There's a you can think of this as some kind of pole, and you tie a rope around. So something is pulling. The weight is pulling on this side, and you pull from this side. This tension is not equal to that tension, okay? TB is not equal to TA. Actually, depending on the friction over here, that TB can be quite different than TA. And we're supposed to show that TB is actually equal to, this is thinner, okay? Is actually equal to TA times e to the minus mu theta, and mu is the static friction coefficient. Okay, so how do you show this that the T has been decreasing? All right, so yeah, actually this is a very tricky problem, right? But it teaches a lot of techniques that we do it in physics. One of the things we do in physics is we look at a tiny piece of it and blow it up and see what it looks like. Okay, so let's blow it up. So a tiny piece, and so this is tiny piece, and over here the tension is that way, and let's see, this is at some, we're going to do some angle theta. That theta, let's call it phi here, okay? Just to send, I'm going to go all the way around there. From here to here, this whole angle is giving theta, okay? So I'm just looking at some point over here, and just a tiny element, and maybe this angle here is going to be very tiny amount. Let's call it d phi here, okay? And so, and we're going to just think of this being symmetric direction here. So over here we can say d phi over 2, and on this side we can say d phi over 2. Now we need to know the forces on this thing, okay? So force is going to be from this pier, right? So of course one will be a normal force, and it's going to be a very tiny amount because this is a tiny piece. You know, the size of this piece is, if this was say r, then size of this piece is that just d rd phi. So on that, how much normal force will be pushing outward, right? It will be, let's call it dn. So this is a small amount, and we expect this to be proportional to that. We don't know yet, but our expectation. So a lot of times physics is like, what do we expect, right? And you know the art of guessing, right? And so this should be, we don't know what it will go over there, but this should be proportional. It will have some force dimension to that, right? Because this does not have dimension. This is just radian. All right. So this will go force dimension. I don't know what force will be. Maybe it will be tension. Who knows? So maybe this side is going to be straight direction. T, but maybe theta is increasing this way. So let's call this side is t, so t plus a little bit more, it's a little or little bit less. It is being positive, negative, okay? We don't know. So over here is t, then we're going to call it this. And so let's look at, so we got these forces, and these forces, and I'm pulling it this way, right? I'm pulling it this way. This is the pull. So we didn't do it right. Let's call this orientation didn't work out right for me. I was thinking something else. Let's redraw this. So it's according to the orientation there. So let's look at this piece. So we're looking at that piece, and this is the direction I'm pulling. Let's call it t plus tt, and that's the direction t, okay? And so these are a little bit curved. It's a little curved. It's not flat, a little curved here. I'll make the curve a little bigger. Okay, so this is the t plus delta t on one end. On the other end is t, and over here is dn. Okay, so if I'm pulling this way, we expect the friction force to opposing me, and it will be 90 degrees to the normal force. All right, so that's the geometry all set up. It's really blown up. So this is d phi over 2 this side, and so if I bring this this over here in the same direction, so there's an angle here. You can see the more this angle, more this angle, and you can translate this. That angle will be d phi over 2. Now the geometry on the other side should work out more or less the same, right? I mean, it's the symmetry. So if you take this vector and translate over here in the same direction, so this is t plus delta t, or dt, t plus dt. This angle will also be so we're gonna do the this is tangent. So this with the tangent will be d phi over 2, and forces are balanced here, right? Forces are balanced. Nothing is accelerating. Then we just need to get a x and y. So this can be our x, and this can be our y, and of course the z is coming out, and that's the way gravity is. So there is also normal on this, like normal 2 is coming out, and these are balancing on the z-axis, which is not important here because everything on the perpendicular to the gravity, we're looking at that, right? So what do we get? In the x, we get fs plus t cosine of d phi over 2 equals to, on the other side is t plus dt t plus dt, d capital T, cosine of d phi over 2, and the y direction get a dn. Dn is equal to the sine of these guys, right? And both of them, both this and this are going to add. So t sine d phi over 2 plus t plus dt sine d phi over 2. And we're going to say fs is, we're going to assume it sort of says max fs. Okay, so we're going to assume that this is a max. I don't think it's said in the problem. So we can say fs max would be mu. This would be also like a small amount because I tuned a small thing. So this should be equal to mu dn. So we got all the formulas except that these guys are all inside the cosine. And so but d phi over 2 is infinitesimal. And then you could say cosine of d phi over 2 is equal to 1 minus d phi over 2 square, right? Plus dollar. And sine of d phi over 2 is d phi over 2 minus 1 over 3 factorial d phi over 2 cube plus like this, right? So now without losing complete, we can say this, I'm not setting it to 0, otherwise I lose all the information, and this one is not setting to 0, okay? So this is just leading order. So this is called taking the taking things in the leading order. When we do approximation, we should keep this. Otherwise, what you will do? You will do, if you can set this to 1 and this to 0. Suppose you do that, then you completely lose information that was the size of the infinitesimal rope you're looking at. So these things, let's see what will become of these things. Oh, let's do over here. Okay, so we have a mu dn. Oh, okay, let's look at number 2. Number 2 first. So get rid of the dn part. Dn equals to t d phi over 2 plus t d phi over 2 plus dt d phi over 2. Now these guys 2 decimals multiplication, and this is 1 decimal, 1 infinitesimal. So we can say compared to these two, this would be 0. When you compare these two, this would be very small compared to that, because t and dt is an infinitesimal compared to t. So this two add becomes t d phi. This should give us a comfort, because remember we were looking, it will be like that. There was an intuition I was telling us. So we got dn, and we can use this in here, and so that becomes t d phi plus t plus equal to t plus dt. So these t's cancel, and we got a dt over d phi is equal, okay, I don't go there, dt over t. Bring that guy and keep it, there's some mu missing, right? There's a mu missing here. This was wondering what's going on. So when I did this guy, I did not use mu here. So also I may have gone into wrong direction, but let's see where does it go. So this is going to be mu d phi. So we said this side was t and this side t plus dt, and phi increases. Did we do it correctly in terms of setting it up? Where's my picture? So we have t this way and t plus del t this way, and we are going to go in that direction. So, and this is the friction and this is the tension. So we expect, let's say we're going to find out. So this is going to be, I think I'm going to go from integrate from TA to TB, because this is a t variable, and this guy goes from theta to 0 because TA is at theta angle. We've gone to all the way theta. That's where the minus sign comes in. Okay, so this is log TB over TA equals to mu phi theta 0 is 0 minus mu theta. 0 minus mu theta. So minus mu theta. Good. Then I exponentiate both sides. That's the way you do the logs, right? TB over TA e to the power minus mu theta. And so this gives me t sub b equals to ta e to the power minus mu theta. Now, I caught my actual, this corresponding to these guys. Now, suppose I've made a mistake there. I would have gotten, with a mistake, I would have gotten, mistake would be, I'll get a TB, will turn out to TB, a TA, e to the power plus mu theta. And if I didn't do integration properly, didn't set the limits properly, and at this point I should definitely say this means the effort I'll have to pull to hold the tension on the other side plus all the friction that helped me. Okay, how come I'm doing more effort on top of the friction? I should have less effort on top of the friction, because friction is helping me, it's not going against me in this. So that you could actually catch your error just by physical intuition. All right, so this is a good problem. Actually, it's a very good problem for all kinds of tests, because you can actually do it pretty fast, and you can also make mistake here pretty fast too. So that's a good problem. And till the next problem, see you. Bye.